If 2 molecules of nitrogen 2 react with 3 molecules of hydrogen 2, determine the number of molecules of NH3 that could form from each starting material. And so basically it's asking us to like do the equation and see how many.
Nitrogen plus hydrogen goes to NH3 ammonia, right?
Yes.
Okay. And how would you balance it?
Let's see. So we put a 3 in front of the hydrogen on the left, and then put a 2 in front of the hydrogen on the right.
So put a 2 in front of here and a 3 in front of here.
Yes.
Perfect. Exactly right. So what's the question say?
It says, determine the number of molecules NH3 that could form from each starting material.
So how many can form?
I'm sorry?
So 1 molecule of nitrogen combines with 3 molecules of hydrogen to give you 2 molecules of ammonia. Does it tell you how much you're starting with?
Yeah, it tells you 2 molecules of nitrogen 2 times blank equals how many molecules of NH3.
Okay. So 2 molecules of this is going to give you how many molecules of this? Multiply everything by 2, right? So if I have 2 nitrogens, I'm going to end up with 4 NH3s. If I had 3 nitrogens, I'd have 6 NH3s. The ratio is always going to be 1 to 2. 1 nitrogen combines with 3 hydrogens to give you 2 ammonias. So if I'm starting with 2 molecules of nitrogen, I'm going to end up with 4 molecules of ammonia. Because 1 molecule of nitrogen gives you 2 molecules of it. 2 molecules of nitrogen are going to give you 4 molecules of ammonia. Does that make sense?
Okay. So you're saying for 2 molecules of nitrogen 2, it would give you 4 molecules of NH3?
Yep.
And then for 3 molecules of hydrogen 2, how many molecules would that give for NH3?
2.
2?
Yeah, 1 molecule of nitrogen and 3 molecules of hydrogen gives you 2 molecules of NH3. That's what your equation says right there.
Oh, okay. I see.
Chapter 8 is on energy. Okay. Energy is measured in joules or kilojoules. Get this here. So energy is measured in joules or kilojoules. That's your standard unit of measurement of energy. And we convert between joules and calories. Anything else that we need to knowing the conversion from the conversion table. So when we're dealing with energy, there's 2 things that make up energy in any kind of system. So the change in energy of the system, because energy is always conserved. So energy is going to equal what's called Q plus W. Q is your heat energy, which is in joules. W is your work energy, which is in physical movement or something, or added to the system. So when the energy changes in the system, you have 2 things changing it. You have heat from energy and you have work from energy. And it's either done to the system or it's on the outside of the system. Okay? So this is your change in energy. This could be Q plus W. Okay? We can measure total energy. So if we look at the text in the text, it says a small sample of propane burns producing carbon dioxide and water vapor. As a hot gas expands, it releases 20 kilojoules of heat. So you release 20 kilojoules of heat, okay, as you're burning the propane, and there's 31 kilojoules of work by pushing against the piston. Okay, so this is Q, this is your heat from energy, and this is W, this is work. Something has moved. Okay, so the total change in energy of the system is going to be 51 kilojoules. Okay. That's how we measure energy. So remember, there's two types. There's energy of heat, and there's energy of mechanical movement. We have physically move a piston or something like that. There's two types of changes. You can have what's called exothermic and endothermic. Okay. Exothermic means energy is released. Endothermic means energy is absorbed by the system. Okay. If you take a test tube and you mix two liquids in it, and the test tube gets hot, that means energy is being released. That's an exothermic reaction. If you grab that same test tube and that test tube gets cold to your touch, that's endothermic. Okay. So think about it. The reaction is going to produce heat. Your hand's going to get hot. That's exothermic. If the heat goes into the system, okay, that's endothermic. It cools it off, depending if you grab the test tube. Exothermic is what's called a delta H. Delta just means change, and H means our enthalpy. Is how we measure these changes. If it's exothermic, delta H is negative. If it's endothermic, delta H is positive. Now, there's no such thing as positive and negative energy. We just use a positive and negative to show which way the energy is being transferred. That's all it is. Okay? And it's impossible to have negative energy because you're never going to create or destroy energy. You're going to transfer it. And the plus and minus is say which way the energy is being transferred. Make sense so far? Okay. So if you look in the book, let's go back here. So it says you have energy plus ammonium chloride. It's going to go to ammonium chloride aqueous. And this was solid, right? Yeah, this is solid. So that's melting. So look where energy is. Is this going to be exothermic or endothermic? What do you think? Energy is being added to the system. It takes energy or heat to melt a solid, right? So this is an endothermic reaction. You're putting energy into the system. If the energy is on the left-hand side, it's an endothermic reaction.
Taking them bowling. I mean, over.
Okay. If the energy is on the right-hand side, it would be exothermic. Energy would be released. Is that making sense?
Yeah.
Okay, perfect. Like I said, I can't see anybody or I can't see any hands or any kind of chat with it. So I just got to speak up so I can if you have any questions. So that's endothermic and exothermic. Let's see what else we got here. Like we have conservation of energy. Energy cannot be created or destroyed. So energy flowing in one direction has to equal the energy flowing in the other direction. You cannot create or destroy energy. That's our law of conservation. That's the first law of thermodynamics. Something happened to my screen here. All right. Okay, are we back? My regular screen again?
Yeah.
Oh, yeah.
Yeah.
Yes. No problem with that going off like that. All right, so we've also got heat and energy, temperature being transferred. We got two things we're going to deal with. We're going to deal with specific heat, which we're going to call SH, and we deal with heat capacity, which is height. So this is our specific heat And this is heat capacity. That's a C. Right? So SH and C. And we have two different formulas that we're going to use for that. In specific heat, we got Q is equal to specific heat times mass times delta T. Delta T just means change in temperature. Okay. Heat capacity, or for the heat capacity, we got Q. Let's see how they're going to put it in this one here. So our Q equals heat capacity times delta T. So the only difference is heat capacity does not involve mass. Specific heat of an object involves the mass of how much you're trying to change. Whereas heat capacity is a property of that compound. So we use specific heat in different. Let me turn this off or it's going to cause problems on the screen. Okay. All right. So using our laws of conservation of energy, we got heat capacity and specific heat. So we can use these to do calculations. You have a table in your book which give you specific heat. I think that's one in your data packet too. They give you a specific heat of certain elements. So using specific heat, we can say how many like one of the examples in your book, that's 8.5. Let's say how many kilojoules of heat required to raise the temperature of 120 grams of water by 5 degrees centigrade. Kilojoules is an energy of heat. Okay. So we have specific heat. So here's our formula. So you know how much energy is going to be required, which is Q. So we take the specific heat of water. Okay, specific heat of water is 8 point something. Where are we at with water? 4.184. So specific heat of water is 4.184, and that's joules per gram centigrade, right? Yeah. So that's joules per gram degree centigrade. That's specific heat of water. Every compound has a different specific heat. Different elements have different specific heats. We can use this in lab to find out what certain bullets are made out of in a crime scene or things like that. So we have the mass, and it said the mass was what? What was the mass of water we were trying to raise? It said 120.0 grams of water. So 120.0 grams of water. And the change in temperature. We said the temperature changed, and it's water by 5 degrees centigrade. Okay, you'll notice grams cancel. You'll notice centigrade cancel, and you're left with joules, which is our heat. And I got to turn my calculator. I don't have a calculator here. You turn this back on, so I have a calculator. So you at 4.184 times 120 times 5. Let's get this turned back on here. Let's see if I set my computer up, I might be able to see. Let me do it this way. Anybody have that answer yet? I think we do that. I'll get mine set up. Please, a calculator.
Yeah, I got 2,510.4.
2,510.4 joules. Okay, so I want to take that, and it wants the answer in kilojoules, right? How many kilojoules of heat? So make sure you answer the question that they're asking. So how many kilojoules of heat are required? So to convert that into kilojoules, so it's 2,510 0.4 joules. And kilojoules, 10 to the 3 joules, right? Kilo means 10 to the third 1,000. So 1, 2, 3, that comes out to 2.51 kilojoules. That's how much heat is required to raise 120 grams of water by 5 degrees centigrade. Let's do another one for an example. Okay. And for example, 8.6, we'll try another one with the book here. Okay. It says when filled with water, a large reactant vessel in a chemical plant has a heat capacity. Okay, so now I got heat capacity, not specific heat. So the heat capacity was Q equals the heat capacity times the change in temperature, delta T. Has a heat capacity of 5.41 times 10 to the 5th kilojoules per gram per degree centigrade. So how many kilojoules are required to raise this entire vessel? I want to raise it from 25 degrees to 48.2 degrees centigrade. So how much heat required? Q is equal to our heat capacity of the vessel, which is 5.41. Times 10 to the 5th kilojoules, 10 to the 5 kilojoules per degree centigrade. That's the heat capacity. That's a given number that you can look up for any material. Okay. That's what is in the vessel. And the change in temperature went from 25 to 48.2. So it changes 48.2 minus what it started at, 25.0. Okay. So 48.2 minus 25.0 is 23.2, right? Degrees centigrade. So we take 5.41 times 23.2. And we went up with 120. So someone do the math of 5.41 times 23.2. That comes out to what? 12,600, something like that. No, it can't be that high. 126.
Yeah, if you round it, but if you don't, it's 125.512.
Okay, perfect. Okay, times 10 to the 5th, right? Bring our exponent right here. And that's going to be kilojoules. So let's put this in 1.26, sign notation, times 10 to the, we move this to 10 to the 7 kilojoules. So 1.26 times 10 to the 7 kilojoules. So that's how we use specific heat and heat capacity in calculations. And we use calorimeters also, like a coffee cup calorimeter. I don't know if you see the picture on your page there. Where it allows you to do different calculations by adding metals to that area or adding different things. And you record the temperature change that occurs. Okay? Record that temperature change. Let's put it on the page here. Okay. Let's get an example here. Let's say, let's do like 8.7 in your book. So let's define specific heat of nickel. Okay. Chemist heats a 26 gram sample to 100 degrees centigrade, places into the coffee cup calorimeter. Coffee cup calorimeter is just a styrofoam coffee cup with a lid on it and a thermometer sticking out of it. So you can record the change in temperature of the water. Okay. Starting with what you're heating your metal sample at 26 grams to 100 degrees centigrade, placing the coffee cup calorimeter that contains 52.1 grams of water. Initial temperature 100 degrees centigrade. After time, the temperature becomes 24 degrees centigrade. That's equilibrium. That means the metal and the water are the same. because things are going to change until the metal and the water reach the same temperature. So you want to find out the Q, the heat transferred from the water, because the Q of the water has to equal the Q of the metal. Remember, energies cannot be created or destroyed. So the temperature that the heat transferred to the water from the hot metal has to equal the heat transferred from the metal, from the water to the metal. Okay. So the heat from the metal going into the water has to equal the heat from the water going into the metal. Okay. So you find a Q for a water. These are two-step problems. Remember, Q equals specific heat, mass, delta T. Specific heat of water is 4.184. That's an 8 joules. Oh man, I can't write here. 4.184 joules per gram degree centigrade. That's water. The mass of water was how much? We said it was, how much water did it have? 52.1 grams of water. 52.1 grams of water. And the change in temperature of the water was, the water went from, what did the water start out at? The water started out, ended up at equal temperature, it ended up at 24 degrees centigrade. And it started out at 20 degrees centigrade. Everybody see where these numbers are coming from? How to set that up? It's 20. It's 20.0. Degrees centigrade. Okay. So we take the temperature change here is 2 degrees. I'm sorry, 4 degrees. Okay, 24 started at 20. 24 minus 20 is 4. So you take 4.184 times 52.1 times 4. That comes out to what? 4 is 200, or 800. 800 and some, right? Who's got an answer for me?
Yeah, so it's 871.4.
871. Okay, and that is that
871.9456.
okay? Perfect. 871, and we're good to 3 significant digits. That's what our weight was here. So 872 joules. These grams cancel, degrees centigrade cancel, and you're left with joules. So that's how much energy is transferred into the water. That's what the water raises. Now, you want the Q of the metal, because that's what we're looking for. It's asking for the specific heat of the metal, right? It says find the specific heat of nickel, which is the metal. It's a 26 gram sample. So Q equals, what's the, oh, find its specific heat. Go back here. So let's rearrange our formula. We're looking for the specific heat of the metal. So specific heat is equal to Q divided by M delta T. Because remember, Q, our formula is Q equals specific heat times M times delta T. So divide by M delta T on both sides, and you get specific heat equals Q divided by M divided by delta T. So the Q value has to be the same because the energy transferred has to be the same going from the metal to the water as it is going from the water to the metal. So Q is equal to 872 joules. The mass of the metal was, what was the mass of our metal? 26 gram sample. And the change in temperature. The metal went from 100 degrees, remember we start that at 100 degrees centigrade, we heat the metal to, right? And then dumped in the water. The water was, and the water ended up at 24 degrees centigrade. remember the temperature that the water ended up with, the water went from 20 to 24. The metal went from 100 to 24. Because at the end, the temperature of the metal and the water have to be the same, or else they keep transferring heat back and forth, which they're not. Okay? So at what's called equilibrium, those have come to the same value. The temperature of the water is the same thing as the temperature of the metal. So 100 minus 24 is 76, right? So what is, and it's degree centigrade. So specific heat is being in joules per gram per degree centigrade. So what is 872 divided by 26 divided by 76? So I need 140, about a quarter, a 0.4 some. So 872 divided by 26 divided by 76 comes out to what?
0.441295555.
Okay. And we're good to, we have three significant digits. So 0.441 joules per gram degree centigrade. That's the specific heat of, and what did you say it was? Oh, nickel. So I wonder if it's in there. Yeah, if you look at the specific heat chart, you see nickel is 0.444, which is really close to what we just got. Okay. Oh. All right, any questions? You will see a question like that on your midterm. I will ask you to calculate either the mass of the metal or what type of metal it is by looking at the chart, the specific heat. But it's a two-step process. It's going to calculate the Q value for water first, because you know the specific heat, you know the mass you're putting into it and the change in temperature. And they're going to use that Q value to calculate the specific heat or some other property for the metal that you put in there. Okay, makes sense? Sort of.
Honestly, not really. Kind
No?
of hard.
Is there any way when you do the problems, because I know they come from word problems, that you could show them so we could get like the whole overall picture of where you're getting the numbers from? Because I know they're in the book and all, but sometimes like you pick random ones, so then I'm trying to see essentially where the problem started from.
Okay, it's I can give you the number it is in the book, if that helps. It's 8.7.
Okay.
And then we can do
Yeah,
it. I'll do another one, write it out. So good. Okay, let's do one and see if we can find out what the metal is. All right, we'll do one. I'll try to write it up a little bit better here. So say you have an unknown metal. You have this block of metal. Okay, so this is a bullet found at a crime scene. You don't know what the metal is. Okay. You weigh it out, and this thing weighs 50 grams. Okay. You heat this metal. You apply heat, and you heat it up to what are you going to heat it up to? Let's say you're going to heat it up to 100 degrees centigrade. Okay, so we good so far? We found this bullet at crime scene. You don't know what it's made out of. You weigh it, it weighs 50 grams. You heat it up to 100 degrees centigrade. And then you're going to take this bullet and you're going to place it. And you have a thermometer right here. Then you're going to place this in the water. Does that make sense so far?
Yeah.
Okay, perfect. And okay, the mass of the water is 50 grams also. That's the mass of the water. That's much water is in that little beaker there. And 50 grams of water at 24.8 degrees centigrade. So it's 50 grams of water and it's at 24.8 degrees centigrade before you put anything in there. When you place the metal in there and the water temperature goes up to, so this water rises to 51, 51.2 degrees centigrade. Okay, so that's what we've done. This is our coffee cup calorimeter. This little beaker right here. It's got a lid on it so it seals it up and everything. All right, so that's the question. Does that make sense?
Yeah.
Yeah.
Okay, 50 grams of metal, we heated 100 centigrade, we dumped it in water, into 50 grams of water. That was at 24.8 degrees centigrade to start with, and the water went up to 51.2 degrees centigrade. And the question might be on the midterm, what is the metal? Okay. Now you'll have a list and you can find the specific heats. We can compare that to see what it is. I hope it's on one of our lists. I don't know, we'll find out. So the first step is to find the heat transferred from the bullet to the water. Because we know if we can find out that, we can find out the heat transferred from the water to the metal also, because it has to be exactly the same. We find a specific heat. Because we know the formula, Q equals specific heat M delta T, mass times change in temperature. And we know we can find the specific heat of the metal, and we can find out what metal it is. Okay. So the first step is to find the Q value for water. So let's take our water. We have that much water and our Q value. So let's find the Q of water. We have the specific heat of water. Specific heat of water is given at 4.184 joules per gram degrees centigrade. That's specific heat of water. The mass of the water, okay, was 50 grams. And the change in temperature of the water was what? What did the water end up at?
51.2.
51.2. And what did the water start at?
50.
Now, what did the water start at? Temperature of the water?
24.8.
24.8. Okay. Sorry. Are you fine? Okay, so now we get, everybody see where the numbers came from? The
Yeah.
4.1 if we looked up at a table for water. Water. All right. So let's do the math. Let's do let's do the temperature of water first. What's 51.2 minus 24.8? What does that come out to on your calculators?
$26.4.
26.4 degrees centigrade. So let's take 4.184 times 50 times 26.4. That's 200 times 24, almost 500. Up, sit down. Someone give me a number.
So you said 51.4 times what?
4.184
Okay.
times 50 times 26.4.
So I got 5,522.88.
Okay, 5,522.88. So 5,523 basically joules. Okay. Everybody good so far? That's the first step. That finds the Q value for water.
Yeah.
Okay. So now we got the same thing. We want to find the specific heat. So again, Q equals specific heat M delta T. Now for the metal, we want to find the specific heat of the metal, so we can identify it. Specific heat equals Q divided by M delta T. We just rearranged it. Solid?
So it's 2 different times, but the bacon on the side and the clothes around. Okay. And there's some chicken wings.
All right.
Sorry, I kept it so long.
That's fine. So what's our Q value? It's the same as the water, right? So Q is 5,523 joules divided by the mass. What's the mass of the metal? What did we say the mass of the metal was?
50 grams.
50 grams. Perfect. And what's the change in temperature? The metal. What did we heat the metal up to start with?
100 degrees centigrade. I mean,
the metal was
100, yeah.
The metal was initially 100 degrees centigrade, and then it went out to what was the final temperature of the metal. Now remember, the final temperature of the metal is equal to the final temperature of the water. That has to be the same. So what's the final temperature of the metal?
4.8.
No, that was the beginning temperature of the water. This is where the water began at. What's the final temperature of the water?
51.2.
51.2. Perfect. So let's do the math. Let's do 100 minus 51.2. Comes out to 48.8, right? That's degrees centigrade. So you take 5,523, divide by 50, divide by 48.8. What does that come out to? Can I get a shake? Can you get a shake?
Are you diabetic?
I got 2.2635
Two- 2.26.
35.
2.26 is close enough. So 2.26 joules per gram degrees centigrade. That's the specific heat of the metal. Then you look on your chart and let's see if we have anything at that range. And we don't. But what you do is you take this number, and when you have it on your midterm, that number will be one of the numbers that matches your data table. And it'll match one of the numbers you can identify what metal it is. So you look at the metals, you see what says 2.26, and if it says it's iron, you put an iron. If it's at gold, whatever it is, just match that number to the metal, and you know what metal it is. That's how the question on the finals on the midterm is going to appear. Does that make more sense now?
Yeah, it does.
Okay. Okay, perfect. Right, so that's how you use what's called a coffee cup calorimeter and use your specific heat. It's a two-step process. Use that any way you want to rearrange that. Let's see. Let's give another good example for you here. Okay, let's go with it. If you want to look at your textbooks, we'll do example 8.9. Okay. It says a heat of a reaction. It says a chemist places a 20-gram sample of ethanol. So 20-gram sample of ethanol. We're going to start with 20 grams of ethanol. CH3, CH2OH. That's ethanol. That's vodka, basically. What you drink. So you have 20 grams of that into a bomb calorimeter with a heat capacity of 28.72 kilojoules per centimeter. So the heat capacity is equal to 28.72. And that is joules, kilojoules per degree centigrade. Okay? When the ethanol ignites, temperature of the calorimeter goes from 22.04. So it starts at 22.04 and it goes up to 42.74 degrees centigrade. How much heat did the ethanol release? So you want the Q value. How much heat did your ethanol release? So Q, remember, this is heat capacity. So Q equals heat capacity times delta T. Okay. So our Q value is equal to our heat capacity, which is 28.72 kilojoules. And then the change in temperature went from, we ended up at 42.74 minus 22.04. So let's do the change in temperature first. So take 42.74. Calculator. I got a calculator back here. Somebody have it yet?
20.7.
20.7. Okay, so it's 28.72 times 20.7. $500.
94.
594. Point, what, point
50.
0.5, yeah, 0.5.
504.
Okay, 0.50. Okay, so that's our, that is in kilojoules. This is degrees centigrade, this is kilojoules per degree centigrade, those cancel. So the energy released for burning ethanol, okay, is going to be 594.5 kilojoules. Now the second
And-
step, well, go ahead.
You got that by multiplying 28.72 and 20.7?
Yep, right here. Q equals your C, which is this value here, and then your delta T, your change in temperature. Delta
Okay,
T
so
just
28,
means-
sorry.
That's okay, go ahead.
So you said 28.72 times 20.7, and that equals 59, 4.5.
594.
Okay. I just want to make sure I got that step down.
Yep, perfect. Okay, then it says calculate. The second step says calculate the energy released in kilojoules per gram of ethanol. A lot of times you do it per gram or per mole, so we use our chemical equation. So we make a second step. So we have 594. So you have to realize what you've got. You got 594.5 kilojoules. And how many grams did we start with? We started with 20 grams. So now you can use this as a conversion number in grams to kilojoules or kilojoules to grams. You set the units up right, and this gives you your kilojoules released per gram of ethanol burned. Then we can convert that to per mole if you want to by grams to moles by the molecular weight, which we did with the last chapter. So 594.5 divided by 20 equals 29.7. So 20 you have 29.7 kilojoules for every gram. So for every 1 gram of ethanol that you burn, okay, you produce 229.7 kilojoules of energy. that make sense?
Yeah, so the 59.4.5 was the amount of heat that was released, and the 29.7 was energy released in kilojoules per gram of ethanol.
Right, this is how much was released when you did 20 grams of it. So divide that by 20 grams, it gives you kilojoules per gram. So for every 1 gram, so in other words, if I burned 40 grams of ethanol, I produce almost 60 kilojoules of energy. Okay, because now I know how many I have for every gram. So if I burned 100 grams, I produce 2,970 kilojoules. So this is a conversion number now. I know for every 1 gram I burn, I am going to produce that much energy. So we use that in all kinds of equations now. As a conversion factor. We can convert grams to kilojoules for ethanol. Or anything else that we want to do the conversions for. Make sense?
Yeah.
Okay, perfect. All right, let's take another reaction and we use what's called enthalpy. Enthalpy is the heat of the reaction. Remember we talked about enthalpy is delta H. That's enthalpy. If delta H is negative, it's exothermic. Delta H is positive, it's endothermic. Okay, let's take a reaction here. Let's see, 1.36. All right, so say we have, let's burn ethanol again. Okay, so let's burn ethanol. And we burn means adding oxygen. And when we burn the present oxygen, it produces CO2 and water. Okay. And we have a delta H for this reaction. Delta H equals negative 1368 kilojoules. Okay, so there's your information. And from this information, they ask the question of how much heat can be released by the combustion of 789 grams of ethanol? So you have 789 grams of ethanol. Is that? Yeah. You can take it somewhere? Okay, 789 grams of ethanol. And we want to know how much heat is produced. Okay. So looking at our delta H, if delta H is negative, is heat being produced on the left side or the right side? If it's a negative value, it's exothermic, which means the test tube gets hot, which means it's going to be plus 1368 kilojoules. It's going to be on the right-hand side. That's kilojoules. Okay, that's an exothermic reaction, releases energy. So how much energy will be released? We burn 789 grams of it. Okay, first thing, what do you have to do as soon as you get an equation? What do you have to do to that equation?
Balance it.
Balance it. So let's balance our equation. We have 2 carbons. Let's make 2 carbons. We have 6 hydrogen. Let's make 6 hydrogen. Oxygens, we have, what do we have on this side? We have 4, we have 7, right? 4, 5, 6, 7. So make this 6 because there's an oxygen right next to it on the other on the ethanol. So that gives you 2 carbons, 6 hydrogens, 6 hydrogens, 6 oxygens, 7 oxygens on the left, 4, 5, 6, 7 on the right. So that's balanced now, right? So that's a molar relationship. That's not a gram relationship. So you got to turn everything into moles. So we have 789 grams. I want to put that into moles. So how many grams per mole do I have for ethanol? Ethanol has 2 carbons. It has 6 hydrogens. And it has 1 oxygen. The carbon is 2 times 12. This is 24. Hydrogen is 6 times 1. Which is 6. Oxygen is 1 times 16, which is 16. Okay. That's the molecular weight of ethanol. So this becomes 46 grams per mole. We have 46 grams for every mole. Okay. So that gives us moles of ethanol. We know 1 mole of ethanol is going to release 1,368 kilojoules. There's our balanced chemical equation, right? So we know if we burn 1 mole, we're going to release 1,368 kilojoules. If I burn 3 moles of oxygen, I'm going to release 1,368 kilojoules. If I form 2 moles of CO2, I'm going to release how much? Or form 3 moles of water. So your balanced chemical equation tells you the relationship of all the different compounds in your equation. So for 1 mole, because remember, if there's no number in front here, it's a 1, right? So 1 mole is going to produce 1,368 kilojoules per every mole. So now I've converted grams to moles and moles to kilojoules. We're using our kilojoules just like we did in the balanced chemical equation. We're using it just like everything else that's in there. So that's going to give you kilojoules of what's produced. Okay. So we need to do 789 divided by 46 times 1,368. Okay. So we have 789 divided by 46 times 1,368. And that comes out to 23,464 kilojoules. Okay, so that's how many kilojoules are released. Ouch. Right on the in the equation, put in sign notation, it's 2.35 times 10 to the, let's see, 1, 2, 3, 4. Make that smaller, make that bigger by 10. Thank you. All right, so 2.35 times 10 to the 4th. You put those back. I don't know why she put them here. Oh, okay. So I'm just gonna knock them over. So 2.35 times 10 to the 4th kilojoules is released from that. Does that make sense? Let's pick another equation. You want to do one more example like that?
Yeah.
Okay, let's say, okay. Let's do an example. Let's say we've got, let's do one that you can figure out the answer. So I'm going to miss sodium chloride, NaCl plus, let's do calcium phosphate is going to form sodium phosphate plus calcium chloride. Right? Does that work out? Calcium phosphate. Wait, that should be a 2. Sorry. One mistake. That should be a 2. Sodium chloride, calcium phosphate, 6, and sodium phosphate, and calcium chloride. All right, there's your equation. Say we're going to mix 5.83 grams of sodium chloride. And say the delta H for this reaction is 78.3 kilojoules. Okay. How much heat is going to be released when we do this reaction? Okay. There's all your information. So now you guys tell me, what's the first step? What would you do first? You saw this on your test. Right after you started crying. No, I was kidding. What would you do first?
Wait, just kidding. Balance the equation.
Balance the equation. You have to balance the equation. Perfect. So there's 3 sodiums there. Let's put a 3 here. There's, what else do we have? 2 phosphate groups. So put a 2 in front of here. That gives you 6 sodium. So let's change this to 6. Okay, 6 chlorines. Put a 3 here. 3 calciums. How's that look? 6 sodiums, 6 sodiums. 6 chlorides, 6 chlorides. 3 calciums, 3 calciums. 2 phosphate groups, 2 phosphate groups. All right, we got a balanced equation. So now we can use in our calculations. We're starting with 5.83 grams. That's what we're starting with, grams of NaCl. We have to convert that into what to use our chemical equation? What do you have to convert into? Chemical equations are all in what type of relationship?
Mole?
Moles. You have to convert to moles. So how many grams are in 1 mole of sodium chloride? We have 1 sodium and we have 1 chloride. Chlorine is 35.5. Sodium is 21. What's sodium? 23. Sodium is 23. So 58.5 grams for every mole. Okay, now we got moles. And we know that for this equation, we know 6 moles of sodium chloride. Because we have this number right here. 6 moles of this is going to produce 783 kilojoules. Because delta H is negative. There's a negative sign above that. We'll sign that. Okay. So we've got 6 moles of NaCl is going to produce, they're going to be 78.3 kilojoules per 6 moles. That's what this means right here. For our balanced chemical equation, it's 78.3 kilojoules for every 6 moles of sodium chloride. If it was calcium phosphate, it'd be 1 mole. If it was sodium phosphate, it'd be 2 moles. It's calcium chloride, it'd be 3 moles. This is our relationship right here, the 6 to 1 to 2 to 3. Okay, that many moles of each one of those compounds is going to produce 78.3 kilojoules. That's what that reaction produced. Okay? That's why this 6 is important down here. That's how many kilojoules is going to be released to run when you run 5.83 grams of sodium chloride into this reaction. So we take 5.83 divided by 58.5 times 78.3 divide by 6. It's on the top you multiply, the bottom you divide. So we got 5.83 divided by 58.5 times 78.3 divided by 6. That equals 1.30 kilojoules. So 1.3 kilojoules is going to be produced when we dissolve 58.3 grams of sodium chloride into calcium phosphate, according to this reaction. That make a little more sense now?
Yeah, a little.
Little,
I don't know why this chapter is so hard. I
it's,
think I'm
it's a
just
lot of new concepts, but go ahead.
yeah, I'm just trying to process all the information.
Did the steps make sense?
Yeah.
That's basically all this chapter has, just the different enthalpies. And you know, if something melts, it's going to be a positive. It's going to be endothermic energy goes into it, right? If you've got a solid, like say we got ice going to water. That's your water. So H2O solid goes to H2O liquid. For a solid, there's bonds holding that solid together. You got to break those bonds. You got to put energy into the system. So energy is going in, not coming out. So energy goes in to break those bonds, so it becomes a liquid. That's endothermic. For the liquid to become a solid, it's releasing energy because those bonds are being formed. When bonds are formed, energy is released. And it's the exact number. So this is minus 45 kilojoules. This would be plus 45 kilojoules. It'd be the same amount of energy. It's just one would be positive, one would be negative. And it's not negative energy. Remember that. It's just the positive and negative sign shows you what direction the energy is moving. Whether it's coming into the system, which is endothermic, which means it gets cooler, or coming out of the system, which means it's exothermic. It would get warmer. And that is pretty much the end of the chapter. Now, let me pull up the questions we had too. There's some questions that were asked. Go over those. Just get my computer running to get I have here real quick. That was this one. Okay. Where was I at? All right, with that, and let me pull up account here, get my emails. Which questions? Yeah. All right, this is on chapter 8. This is one of the problems they sent in here. It said that there is use the heat of the solution to calculate the molar heat of the solution for potassium hydroxide. I'm not sure which question this was. They're one of the different ones there, though, because everybody had a little different numbers. But it gave you the mass of water, which was 70. Okay, let's write this down. Let me get a screen back here. All right, so it says the mass of water was 70 grams. The mass of potassium hydroxide was equal to 5 grams. The temperature change gave you, this must have been from one of the labs, gives you a temperature change equal to 17.55. Lousy 7. Okay. And it says calculate the amount of heat gained or lost by the solution. So you want the Q value, right? Remember, we talked about Q equals specific heat, mass, delta T. And this is a solution, so solution is the water. And you want to know the amount in kilojoules of the heat gained or lost by the system. So what's the specific heat of water? Remember, it's 4.184. Again, you can always look that up. 4.184 joules. Gosh, I'm terrible at writing J's on this computer. Per gram degrees centigrade. Mass of water was 70 grams. And the change in temperature was 17.55. So 4.184 times 70 times 17.5 comes out to 5140 joules. And it wants it in kilojoules. So we take joules. Kilojoules is 10 to the 3. So we're going to multiply by our exponent, you bring it up, change the sign. So 10 to the negative 3. So the decimal point 3 places to the left. So 1, 2, 3, 5.14 kilojoules. It tells you the heat gained by the water. Just using our formula, specific heat mass delta T. And then it wants to calculate the molar heat of the solution of potassium hydroxide. So it wants you to know how much kilojoules per mole released. It says it wants to calculate the molar heat of the solution for potassium hydroxide. So how much heat 1 mole is going to release? So we know there is 50 grams, right? Or I'm sorry, 5 grams. So we're going to start with 5.00 grams of potassium hydroxide. That's this number right here. And we can convert that into moles because it wants the molar heat. So we convert this into moles. And potassium hydroxide is 1 potassium, 1 oxygen, 1 hydrogen. And they give you an equation that says 56.105 grams per mole. So 56.105 grams per mole. Okay, that was 1 potassium, 1 oxygen, 1 hydrogen. So 5 divided by 56.15 comes out to 0.0891 moles of KOH. Okay. So when we added 5 grams into our solution, we added 0.0891 moles of that solution. Okay. And you want to know how many, you want to do the molar heat of it. So how many kilojoules per mole? So we know that solution released 5.14 kilojoules, and it was per 0.0891 moles. That gives you kilojoules per mole. So we know 1 mole is going to give you half as many kilojoules. So we take 5.14 divided by 0.0891, okay, and that comes out to 57.7. It pumps out with you for a minute. So you have to go potty. And then you put it back in here or back in the house, either way.
Should I, wait, where's the station?
You'll listen to it.
Oh.
Yeah, just gonna go potty. Okay, go out. All right, so 57.7 kilojoules. Thanks, Izzy,
Yeah, of course.
per mole. That is how much energy is released when you burn 1 mole of potassium hydroxide. And it asks for the molar heat of the solution. So how much heat is generated per mole? That was one of the questions. Does that make sense? We'll get some good practice at doing some of these here. The other question was, the system gains 657 kilojoules of heat. So you have a system, okay, you have this little box, and it's going to gain 657 kilojoules, okay, of heat. Delta means heat also. Okay. Resulting in an internal energy equal to, get the next one? Make sure we're doing this right. Yeah, let's take one. So the system gains 657 kilojoules of heat. That's how much it increases by. It results in a change of internal energy of 186 kilojoules. Okay. So the energy of the system let's get something here. No, I don't think I did. Okay. So remember the energy of the system. Okay. We talked about energy is equal to heat energy and work, right? And we said energy was equal to work, physical work by moving a piston plus the heat. Okay. So this tells you that the energy the system it gained 657 kilojoules of heat. So you've gained 650 kilojoules of heat. That is our Q value, right? That's how much heat you gain. The change in internal energy of the whole system is 186 kilojoules. That's how much the energy changed. So we rearrange this. We're looking for how much work is done. So work is equal to energy minus Q. Right? Just rearrange this formula. So we're looking for how much work is done. The total change in the energy system was 186 minus 657, which is our kilojoules. Both those are in kilojoules. So the total work on the system comes out to be 471 kilojoules. And again, the negative sign, there's no such thing as negative energy. The negative sign just indicates which direction the energy is flowing. So the difference between these two numbers is 471 kilojoules. So the work done on the system had to be 471 kilojoules. Okay. So that would be your answer for the work. And then it says, was work done by the system or was work done on the system? What happened? Where did the energy go? I told you the question. The system gains 657 kilojoules, resulting in internal energy of positive kilojoules. Okay. So work was done. Was it done by the system or on the system? Okay, so you gained energy, you gained heat, you didn't release it, you gained it, and internal energy to 186. So you've increased the internal energy. So it would work on the system. This is work that's going on the system. So the energies come in. I'm going to word this right here. So your total energy was gained by the system. Okay? You got 657 joules worked on it. So the other had to go out. So the work done, the W, was done by the system. That allows you to have a lower number here, a lower number of energy. In other words, your energy was 186 kilojoules. You put in 657. So that means the rest had to go out. This 471 had to go out as work done by the system to its environment. Okay. When your value coming in is greater than the total energy, the work had to go out of the system to deplete that down to the 186. And so that would work done by the system. And we had another one on specific heat, which is a really good, you'll see something like this on your midterm. So let's go to the page. And it says the temperature of a sample of aluminum. So you have a block of aluminum. This is aluminum, okay? The temperature of a sample of aluminum increased by 23.3 degrees centigrade. So increased by 23.3 degrees centigrade. When 275 joules of heat was applied. So you applied 270, what did I say, 5 joules of heat. And it wants to know what is the mass of aluminum. All right, so this is what the question says. You have a block of aluminum. Okay, the heat was increased by 23.3 degrees centigrade. That was the change in temperature. It's give you the change, not what it starts at was, but the change. And it gave you the energy released, energy absorbed by it was 275 joules. That's our Q value. So we know Q equals where am I at? Specific heat, M delta T. So we're looking for mass. So M is equal to Q divided by specific heat delta T. What's the Q value you're given is 275 joules. Specific heat, what's the specific heat of aluminum? There's a chart on the side there on the question. It'll be a chart for your test too. It gives you specific heat values. Specific heat of aluminum is 0.903. So 0.903 joules per gram degree centigrade. And the change in temperature was 23.3 degrees centigrade. Grams, joules cancel. Degrees centigrade cancel. This is per gram. You're left with grams. Okay, we're just filling in our formula right there. We're looking for mass. We're given the specific heat from a chart. We're given the change in temperature, and we're given the Q value, the amount of heat absorbed for that change to occur. So 275 divided by 0.903 divided by 23.3 comes out to 13.1 grams. That's the mass of your sample. Is that making sense, everybody? They can follow along with the problem. Any questions on it? Go on to the next problem. Our next problem has 2 steps, right? Yeah, we have 2 steps. It says potassium nitrate has a molar mass of 101.1. That's KNO3, 1 potassium, 1 nitrogen, 3 oxygen. In a constant pressure calorimeter, 31 grams is dissolved in 315 grams of water at 23 degrees centigrade. Okay, so let's write it down. So we have potassium nitrate. That's what we're starting with. Okay, so potassium nitrate, and we know that it gives you the molar mass: 1 potassium, 1 nitrogen, 3 oxygens. Open the screen first. All right, so they say the molar mass, the molecular weight of potassium nitrate, and it gives you at, or was it 101.1? 101.1 grams per mole. That's our molecular weight. They calculated for you. 1 potassium, 1 nitrogen, 3 oxygens. We start with 31.0 grams of it. So we're starting with 31.0 grams and dissolve that in 315 grams of water. The water is at 23.00 degrees centigrade to start with. So everybody understand that so far? We're taking 31 grams of potassium nitrate. We're dumping it into 315 grams of water, and the water is initially at 23 degrees centigrade. The temperature goes up to temperature decreases. I'm sorry. Okay, the temperature decreases to 21. So the temperature, after they add it to it, decreases to 21.00 degrees centigrade. Okay. It says assume that the resulting solution has the same specific heat as water. Okay, how much heat was released by the solution? So we're going to take our solution. And we know we have Q is our heat released by the solution. Specific heat M delta T. Specific heat of water is 4.184 joules per gram degree centigrade, right? The mass was 315. And our temperature chain went from 23 to 21. So 2.00 degrees centigrade. So there's our specific heat. There was our mass. And there was a change in temperature.
I'm sorry, is the mass 31.0 or is it 31?
The mass of potassium nitrate is 31. The mass of the water is 3 to 15. We're talking about the heat. We're talking about the heat of solution of the water going up.
Okay,
So the water. What's that?
I didn't see the 315,
Oh, okay.
so that
Okay,
makes sense.
perfect.
Thank you.
Okay, so the specific heat of water is 4.184. The 315 grams of water and it changed 2 degrees centigrade. Okay. So 4.184 times 315 times 2 comes out to 264 joules. Or 2,000, where am I at? 2,000, roughly 2,640 joules. That's our Q. And we want in kilojoules, it says, so it is, move it in 3 places, 1, 2, 3, 2.64 kilojoules. So that is our heat relief. They want to know the temperature resulting decrease. How much heat was released by the solution? 2.64 kilojoules. And what is the enthalpy of the reaction? The enthalpy is kilojoules per mole. So we got to convert this here. This is 31 grams. We got to convert that into moles. And then it's moles per kilojoule. The kilojoules per mole of what it released. That's our enthalpy. Remember delta H. So you got to convert our 31 grams potassium nitrate. And we know there's 101. It gave us that 0.1 grams per mole. We could have figured that out on our own though. Okay, that gives us how many moles we use. So 31 divided by 101.1 came out to 0.3. Did you? Go back through. Okay. 0.307 moles. That's how many moles we use in that solution. So our total solution went from 2.64 kilojoules for every 0.307 moles. That is going to be our change in enthalpy, or delta H, in kilojoules per mole. So 2.64 divided by 0.307 comes out to 8.60 kilojoules per mole. That's the second part of it. That's the enthalpy of the reaction. It's positive because energy was absorbed. This is not negative. If energy was released via negative value and it was absorbed by this, that's where the temperature went down. Energy was absorbed. It went from 23 to 21. So that's an endothermic reaction. So its enthalpy is going to be a positive value, 8.6 kilojoules per mole. So far, so good. All right, let's do it. It says this one is a, consider the reaction. This is iron 3 oxide plus, or I'm sorry, iron 3 oxide decomposes into iron and oxygen. Okay, So whenever you see an equation, it says delta H equals positive 824.2 kilojoules. So when you see a, what's the first thing you'd want to do when you see a chemical equation?
Balance.
Balance it. So let's balance it. So 2 irons, 2 irons, 3 oxygens, 2 oxygens. So we have to make this 6. So make that 3, make that a 2, and we make this a 4. How's that look? Does that look right? 4 irons, 6 oxygens, 6 oxygens. All right, so now we got balanced chemical equation. Now it's going to ask you a question about this thing. It's going to say the formation of 54 grams of iron results in, and you got to pick the right answer. So you got 54.0 grams of iron. All right. Now it says the answers are absorption of 11,100 kilojoules of heat, release of 797 kilojoules of heat, absorption of 199, release of 11100, absorption and release. We can calculate what it is. We want to know how much heat is going to be either absorbed or released by this reaction. Remember, this is a positive value here. Okay? So positive value means energy is being absorbed, right? Because negative delta H is your exothermic. That means it's, your test tube is getting hotter. This is energy is being absorbed by the reaction. Test tube is getting colder. So the energy is on the left-hand side. So you know you can eliminate all the ones that say release. So energy is being absorbed. Now, how much energy is being absorbed? There's a molar relationship, right? So what do we have to convert our grams into? We have to convert grams into moles. So you can look at our chemical equation. And iron weighs 55.845 grams. Okay, so 54, I don't need the equal something yet. So now we got moles of iron, right? Everybody looking at the periodic table, they can see 1 mole of iron weighs 55.845 grams. Okay, now we got moles, and we know how many moles of, what was the question asking? It was asking for iron, right? We show it 54 grams of iron. So we look at iron, there's 4 moles of iron in our balanced chemical equation, right? So we got 4 moles of iron is going to absorb 824.2 kilojoules. That's what it says right there. And there's our number. It says 2 moles of iron 3 oxide, or 4 moles of iron, or 3 moles of oxygen. Right? It's going to absorb 824.2 kilojoules of energy, of heat. So since you're with iron, we have 4 moles of iron per every 824.2 kilojoules of heat. So our grams of iron cancel, our moles of iron cancel, and we're left with kilojoules. Okay. And that comes out to roughly 199 kilojoules. It's being, and is it being absorbed or released? It's being absorbed, because delta H is positive. So look on the chart, you'd see the one that says the absorption of 199 kilojoules of heat. And that'd be the one you have, the one you would select. Okay. And there's one more here for this set of questions. Then there's another set of questions to go over, and then we can open up to any other questions. Okay, so far so good. Any questions on those?
No.
Perfect. I know they're kind of strange ones to do, but you get it as you go along. And I'll work through more examples if you want. That's not a problem. The other example says sodium metal is added to hydrochloric acid to produce. Okay, so sodium metal, I'll give you the formula. Sodium metal is added to hydrochloric acid, HCl, that's a C, to form sodium chloride and hydrogen gas. Okay. So we look at that. What's the first thing we got to do with it?
Balance it.
Balance it. So let's see, two hydrogens gives us two chlorides, two sodiums. Is that right? Two sodiums left, two on the right. Two hydrogens on the left, two hydrogens on the right. Two chlorines on the left, two chlorines on the right. Now that's good. Okay, so your balanced chemical equation. Now you're going to have 8.42 grams of sodium metal. So we have our sodium metal. We have 0.8, what's it, I said 42 grams. Okay. Is added to a bunch of hydrochloric acid. 8,750 joules of heat are produced. So the delta H equals negative. Heat's being produced. Remember, heat's being released. It's exothermic. Energy's on the right-hand side. So it's negative 8750. 8750 joules. Heat are produced. What is the enthalpy of the reaction? Okay. So you want to calculate the enthalpy. I should have wrote it this way. Plus 8750 joules. Okay. So that much is being released. That much heat when we add 8.42. Okay, so we got to convert our 0.842 into moles because we need a molar relationship. And then this chemical equation says 2 moles of sodium. Okay, so 8.842 moles. 0.842 grams. Okay. Okay. Convert that into moles. We know we have 23 grams, right? Sodium. 23 grams per mole. So we know this is going to be, that 8.42 grams is going to be divided by 23 is 0.0366. Yeah. 366 moles. That's how many moles we added here. And this is how much heat was released when we added that many grams. Okay. So we know we have 8,750. It's joules or kilojoules? Joules per every 0.0366 moles. That gives us joules per mole. And that comes out to 239 2,390 joules per mole, right? 8,750 divided by 0.0366. Comes out to 2,300, 23,000. Right? Comes out to 23900. Let's see, this is 239. $239,000 joules per mole. Is that what you guys got? I'm trying to do my math right. Is that what everybody else got? Let me double check it here. 239, it's 8,750 divided by 0.00366. 239,000. I'm still doing something wrong there. All right, 8,750 divided by 0.0366 equals 239,071. Let's do this like this. 239,071.
Oh, you didn't see the back.
0.038. That's exactly what it comes out to. That's joules
I think Amy has the same.
per mole. Okay,
I didn't know.
and you want this in kilojoules because you're asking for kilojoules per mole. Okay, so we convert that into kilojoules. We were decimal point 3 places, right? 1, 2, 3. Comes out to 239 kilojoules per mole. That makes sense? It's gonna keep your zero straight. You're doing those multiplications. So far, so good.
Yeah.
Okay, that's not the answer. That's how many joules per mole we have. Because it's asking you, what is the enthalpy of that reaction? Okay, so there's 239 joules per mole. Now in this reaction, this was 0.0366 moles of sodium. How many moles of sodium do we have for the reaction? In our balanced chemical equation, we have 2. So we have 239 kilojoules for every 1 mole. So for 2 moles, the delta H for this reaction is going to be negative because it's being released, and it's going to be 239 double because there's 2 moles now, not 1. We have 239 kilojoules for every 1 mole, so we're going to have 478 kilojoules for 2 moles, right there. Okay. So your answer to the number of enthalpy is going to be negative 478 kilojoules.
I'm sorry, how did you get that?
Okay, are we good to this point? Right here. We calculated there was 239 kilojoules per every mole. How many moles of sodium are in our balanced chemical equation? There's 2, right?
Yeah.
Okay, so if you had 10 kilojoules for every mole and you had 2 moles, how many kilojoules? You have 20, right? We have 239 for every mole, and we have 2 moles. So we have 478, which just doubled our 239.
Okay, got it.
So this is times 2 because of our sodium. Does that make sense?
Yeah, it does.
Okay, perfect. Those are good questions. Those are real good questions. We got one more set of questions here. All right, this one says, this is doing limiting reagents. And it says if you have 30, okay, you're making sandwiches, you're making cheese sandwiches. I don't know who likes cheese sandwiches, but that's okay. For every cheese sandwich, it takes 2 slices of bread and 3 slices of cheese. Okay. So 1 sandwich is 2 slices of bread, 3 slices of cheese, put together to make a sandwich. Okay. You have 32 slices of bread, and we have 45 slices of cheese. How many sandwiches can you make? Okay. If we use the bread, we have 32 slices. So with the bread, we can make 16 sandwiches. With the cheese, we can make 45. You need 3 for every sandwich. We need 15 sandwiches. Right? Because there's 3 pieces of cheese in every sandwich. If you have 15 sandwiches, you've used up your 45 slices of cheese. Okay? You have 32 slices of bread. You could theoretically have 16 sandwiches. At 15 sandwiches, we're going to run out of cheese. So your sandwiches are going to stop. So the total amount of sandwiches you can make is only 15. Even though you got enough bread for 16, you only got enough cheese for 15. So the cheese is our limiting reagent. We're going to run out of cheese first. Once you run out of cheese first, you can't just give bread sandwiches. People don't like that. Okay, you got to put the cheese in there. So you can only make and sell a total of 15 cheese sandwiches. So the number of sandwiches you can make is 15. It says, which of the 2 ingredients limit the number of sandwiches that can be made? It's going to be the cheese, because you're going to run out of that first. Now, what quantity of ingredients in excess remains? So does any cheese remain?
Yeah.
What's that?
Yes.
No, you used up all the cheese, right? You had 45 slices of cheese, you made 15 sandwiches. So you used up all the cheese, now we stop. So all the cheese is gone. Okay, we made 15 sandwiches, all the cheese is gone. So what's left over? Is cheese or bread gonna be left over?
Bread.
Bread, how many?
Would it be 16?
We used 15 sandwiches, so we've used 30, right? And we had 32. So we'd have 2 slices of bread left over,
Hmm. Okay.
right? Does that make sense?
What chapter did they get that from?
It came from one of the homework questions. It looks like question 23 of 30. But like your numbers will be, everybody's numbers will be different.
It was from a lab.
Oh, it's from the lab? Okay. So does that make sense now, though?
Yeah.
Okay. Perfect. Cool. And it says the video shows aqueous sodium chloride. They're adding sodium chloride. So let's write it down. Sodium chloride, this is another lab it look like. Sodium chloride to aqueous silver nitrate. AgNO3. Okay. That doesn't look good. Let me get that right. Boy, where'd the line come from? There we go. NaCl plus silver nitrate. So we know it's going to be a double displacement reaction. So we're going to form NaNO3 plus AgCl. Okay, so there's a reaction. That's what happens. It forms a precipitate. Write a balanced molecular equation for the reaction. Okay, so this is aqueous. This was aqueous. Those are liquids. This is going to be aqueous, and this is going to be a solid. How do I know that? I look at my solubility chart that I gave you in the data packet. You look up sodium and nitrate. You draw the line between the two. It comes to aqueous. Look up AgCl. It is a solid. So let's do that. Let's look at my table. Okay, there's my table. Here is sodium. Where's sodium? Sodium. And here is nitrate. Okay, we drew between the two. Sodium nitrate is aqueous. Okay, let's look for silver. And let's look for chloride. Silver chloride is solid. That's how I'm getting those values right there. Okay, that's where these come from, aqueous and solid. You know the first you're aqueous because you mix 2 clear liquids together. There was no precipitate, no solid. So there's your, that's your equation. Is that balanced?
Yeah.
Perfect. Balanced for you. Piece of cake. 1 sodium, 1 sodium, 1 chlorine, 1 chlorate, 1 silver, 1 silver, 1 NO3 group, 1 NO3 group. You got it. So there's your balanced molecular equation. Okay, that's what it should say. And the next one says,
Wait, that was it? That was the answer?
it's well, that for that question, that
Oh.
part of it. Oh, that's it. That's all it said, huh?
Oh.
Okay, let's take it a step further, because what I would do in your test is I would say, write the total ionic and then the net ionic, and then identify your spectator ions. But that's the balanced molecular equation. Now the total ionic equation is Na plus Cl minus plus Ag plus NO3 minus goes to Na plus NO3 minus plus AgCl. That does not break apart. That's your solid. So this is your molecular bounds. This is your total ionic. And then we want your net ionic. The net ionic means removing the spectator ions, which are the same on both sides. I didn't want to do that. Na, NO3. So your net one is Cl minus plus Ag plus goes to AgCl. So there's your molecular on top, your net ion, your total ionic on the middle, and your net ionic on the bottom. Okay? And what's crossed out, the sodium and the Na plus and the NO3 minus are your spectator ions. That's what you'll see on my test. But for the one I just asked you, that was it.
Okay. I don't really know how to determine the charges. Is that included in the chart?
Look at your periodic table. The first, this is how we do our charges. Charges are always determined right here. Everything in this row here is +1. Everything in this row is +2. Everything in this row is +3. Column, I should say columns. Okay, everything in this column is neutral. That's our neutral column. These are -3, -2, -1, and these are 0. That's how you determine charges of any element.
Okay.
Okay, and when you have a polyatomic ion, it's determined by the polyatomic ion chart. Like we have NO3 in there. NO3 has a negative charge, -1. If it's SO4, it would be -2. NH4 would be +1. Okay, all your charges are right there. So if it's a polyatomic ion, you look here. If it's an element, you look on the chart and use those columns. Does that make sense now?
Yes. Thank you.
Okay. Oh, no problem. No problem at all. Okay. But the question I want to ask was just write this. That's all I wanted. But I would ask you for more than that. All right, that's once the electron configuration for zinc. Look on your periodic table, look under zinc. Where's zinc? Zinc is, let me get my periodic table here. Zinc is in the, where are we at? Everybody sees zinc. Zinc is number 30 on your periodic table. So zinc, let's go to periodic table. There, zinc is right here. So we're going to write our electron configuration. Start at the top, 1s2, 2s2, 2p6. So this is 1s2 right here, across the top, 2s2, 2p6. Let me drop down, 3s2, 3p6. That's 3s2, 3p6, 4s2. Okay, then we're going to go to 3d, because remember D's all, this is our D's right here, and D's all start with 3. So this is 3d9, because this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 3d10, I'm sorry. I thought it was one short, 3d10, because there's 10 across. Right? So it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. We stop right here. Now you also have to write the noble gas core abbreviation. Noble gas core abbreviation, back it up. Go backwards to the nearest noble gas. That's argon. So you put argon in parentheses. That can all it, and then you continue. 4s2, 3d10. So the top one is the full electron configuration. The bottom one is the noble gas core abbreviation electron configuration. Okay, perfect. So that's your electron configuration for zinc. And it says classify monoatomic and polyatomic ions. So let's do this list. Let's do monoatomic. Mono means what?
1.
Poly means what? More than one, right? Mono means one, poly means more than one. So if we have, I'm going to put a list of all the ones down here. We have Li plus, we have H3O plus, we have I minus, OH minus. We have IO4 minus, we have NO3 minus. We have Mg2 plus, we have Cu2 plus, we have iron 2 plus, we have sulfur 2 minus, and we have mercury 2 plus. Okay, let's start with lithium, Li plus. Is that monatomic or polyatomic? Is there one atom or two atoms, or more than one?
Would it be one?
Yeah, lithium would be one. Li plus would go under monoatomic. H3O plus, is there more than one type of element, atom there?
I'm sorry, for which one?
H3O plus, where's that one go?
Polyatomic?
Polyatomic. There's hydrogen, there's oxygen. I minus, monatomic or polyatomic?
Monatomic.
Okay. OH minus, hydroxide ion, would be,
Monatomic?
how many? There's an oxygen, there's hydrogen.
Oh, polyatomic. Okay,
Polyatomic. Is that making sense now?
I got it.
All right, so IO4 minus, right? Where's the NO3 minus gonna go?
Polyatomic.
Polyatomic, perfect. Mg2 plus,
Polyatomic.
monatomic, right? Copper 2 plus, monoatomic. Iron 2 plus,
Monatomic.
got it. Sulfur 2 minus,
Monatomic.
and mercury 2 plus,
Monatomic.
got it.
Okay, that makes sense. I didn't
That
really.
makes sense?
Yeah.
Yeah, just you gotta realize what they're asking you. Yeah, whether it's one atom or more than one atom, different type of atom. And that was it. All right, other questions? That's all the ones that have been sent in. So we covered all those. We covered the chapter. Other questions? I know it's a holiday. Well, it's the official holiday. But everybody have a good 4th of July?
Yeah.
Cool. All right.
I have a question about the midterm.
Okay, shoot.
Are we able to skip questions and go back, or is it like you have to answer right there to go to the next question?
You can answer questions in any order you want. Skip and go back. Yes.
Okay, great. Sounds good.
Yep. You'll have 3 hours and 10 minutes, and you can take it anytime during the day, that 3-hour block, whatever is
Okay.
best for you.
Okay, thank you.
You're welcome. No problem. Any other questions on the midterm or anything else?
Question in regards to the final. Does it include these chapters?
Yes. Final will be cumulative. It'll be about 10 to 15% of this stuff, and then all the newer stuff will be the most of it. But it's gonna be, because when you think about it, it's all gonna build upon this stuff. We're still gonna use conversions. We're still gonna use significant figures. It's gonna build upon each thing. So it will be cumulative. About 10 to 15% will be from this midterm. But you have built-in study guide, you have your midterm with it. So yeah,
Okay.
okay.